Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have a trio today. We have Valentina Penza, Serena
Hi.
Criscuoli, and Francesco Berrilli. Hello there, Valentina, Serena, and Francesco.
Hi, Frank.
Let's see, let's start off. It is December 17th of 2024 as we record this, and we are coming up on solstice. And so I'm in Phoenix, and we are definitely in our winter mode. So we get a little chilly in the morning, and then it heats up very nice in the afternoon. So it's lovely. And I'm going to guess you three are in Italy somewhere. Where are you at? What's your geolocation?
In Rome. We're in Rome.
Rome, very nice.
Department of Physics at Vergata University.
Cool. Does Rome get snow? Do you get snow in Rome?
No, not typically.
Snow. Okay.
No.
But chilly.
Yeah. I live in Colorado and just came in for the night, and it's very warm for me right now here.
It would be snowy where you're at.
Yeah, we had a kind of warmish year so far. So I didn't see any snow in the forecast in the near future. So we'll see.
Cool.
Yeah, but she was student in Tor Vergata, in Rome, Tor Vergata University.
Very cool. Very
I'm
cool.
back to my
Master and PhD.
yeah. So I'm back to my alma mater.
Now you're back visiting, so it's all good.
We are very happy. Yeah.
Cool. Okay. Let's start with Valentina. And Valentina, what do you like to do for research?
My interest in solar physics, Francesco and Serena, in particular spectral line formation, radiative transfer, and irradiance of solar variability.
Cool. Serena, how about you? What do you like to do for research?
Yeah, so first of all, I'm a scientist working at National Solar Observatory, and I work for DGIST, Daniel Kane Solar Telescope, which maybe some of you already know. It's the largest solar telescope ever built. And I'm involved in different aspects of operations, but I also, as for science, I also like doing solar irradiance reconstructions, and in particular, I like to work on the radiative transfer aspect. So,
very good. Cool. Very nice. And Francesco, what do you like to do for research?
I'm professor here at the Rome Tor Vergata University, and I started to study star formation because now I was interested in the life of stars from my teenager age, a lot of years ago. And then I moved to solar instrumentation for ground-based telescopes.
Okay.
We work in Tenerife, the Canary Islands, for an Italian-French telescope at the beginning of 2000. And then I moved in solar image data analysis and TSI, so total solar irradiance. And now I move a little bit toward the interaction between the sun and the planet. So we move from star to Earth. So it's okay.
That's right. That's right. Very good. Very nice. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. So you can go grab a copy for free. Go get one. Reconstruction of the total solar irradiance during the last millennium. And Valentina, Serena, and Francesco, take us away.
Yeah, I think
I would like, if possible, to introduce the other authors. Because there is also Luca Bertello, currently scientist at the National Solar Observatory in Boulder. He's an expert in long-term magnetic field evolution. And Matteo Cantoresi, he's a postdoc here in the Roma Tor Vergata University. He's an expert of photospheric magnetic field, and in particular, he studies corona holes. So the connection between the photospheric magnetic field and the production of the corona holes is important for fast solar wind interaction with the Earth magnetosphere, aurora, and so on.
Yes.
Lorenzo Lucaferri, she's a PhD, a young PhD student, again, here in Tor Vergata in a collaboration with Exeter University and Trento University. She's a climatologist and collaborate for Sun-Earth interaction.
Cool.
We want to use this data reconstruction to study the past of the planet. Raffaele Reda is a postdoc here in Vergata and work in the field of interaction between solar wind and planetary atmosphere. He's an expert in data analysis. And finally, Simone Uzeka is a scientist at the Institute of Computational Life Science in Zurich, and is an expert in machine learning techniques, data analysis, and he works with Jorge Beer group for the reconstruction of the solar potential from cosmogenic isotopes in 3 rings.
Cool. Okay. Very nice. Good shout out. Good shout out. Okay. Let's go ahead and get into it.
Okay, so first of all, I would like to introduce what we mean with solar irradiance. Solar irradiance is the energy that is emitted by the sun in the form of electromagnetic radiation that arrives on top of the Earth's atmosphere, and is also measured sorry, the energy that for surface area and in time.
Yes.
With the term total solar irradiance, we mean that the irradiance integrated over the whole spectrum, and which is the focus of the article. But we also distinguish between total solar irradiance and spectral solar irradiance, which is instead irradiance integrated over specific wavelength ranges.
Okay.
So we started monitoring solar irradiance about 30 years ago through the use of instruments aboard of satellites. And these measurements allowed us to discover a few important things. The first one is that the total solar irradiance is not constant. Before these measurements, it was very debated whether solar irradiance was changing or not, up to the point that it was called also the solar constant. But we know through these measurements that it's not constant at all. It varies on different temporal scales. In particular, we know that it varies in phase with the activity cycle, with the 11-year activity cycle.
Cool.
The other important thing that we have learned is that these variations are modulated by the passage on the disk of magnetic activity of active regions. So we know in particular that sunspots tend to decrease total solar irradiance, while flash contribute in a positive way. And what we have during what we measure along the solar cycle is basically the results of these two competitive effects.
Cool. I'm with you.
So the thing is that we know for long we have had some clues, and after this we started from Foucault in the 1800s. He already had this idea that the energy emitted by the sun has an effect on the Earth's atmosphere. And so that this is why we start monitoring these variations. And so we know now that after these variations of energy over time affect the Earth climate. And so in order to inform climatologists what these effects are, we need to compile very long data sets, very homogeneous data sets that they can then use as an input to their models. Cool. So now the problem is that we only have records for 40 years, and so we have to send back these DSI variations. And the way we do that is that we necessarily have to do it through models.
Okay.
So all the models, as I said before, they're based on this empirical evidence that DSI is modulated by magnetic activity. But unfortunately, our direct measurements of this magnetic activity started basically around the end of the 1800s.
Yeah.
And so if you want to extend these estimates back, we need to rely on what we call proxies.
Yes.
In this particular work, in this article, we used the open flux, solar open flux, and Francesco will talk more about it.
Cool.
Yeah,
okay. I'm with you.
The problem is, if you want to reconstruct the solar activity in the past, in the very far past, we need some proxy, and the only way using data is to use the cosmogenic isotopes. So what happens when the galactic cosmic rays, so particles coming from outside our solar system, arrive on the heliosphere, interact with the Earth atmosphere,
Yes.
produce particular isotopes, for example, carbon-14 or beryllium-10,
Okay.
and we can recover information about the past of the solar activity, counting the ratio of these particular isotopes with the normal beryllium, normal carbon.
Yes, I'm with you.
And why we can study the solar modulation using this cosmogenic isotopes? Okay, because the solar modulation potential and open field are strong correlated, are more or less connected because there is an interaction between the flux of cosmogenic isotopes produced by cosmic ray and the magnetic field in the heliosphere. When the magnetic field increase, because increase the solar activity, the number of galactic cosmic rays decrease.
Yes.
Then we have an inverse correlation between the solar activity and the number of isotopes. So we invert this correlation and we reconstruct, or we can try to reconstruct the solar activity in the past.
Got it. Very cool. Very cool. Good.
The comparison is in the figure 1. So in the figure 1, we can see the modulation. Exactly. This is the modulation of the two proxies. So the open solar magnetic field and the solar modulation potential, we can see are very similar. And then we can use this reconstruction to recover the behavior of the sun in the past.
Cool.
The correlation is explained in the figure number 2, where we can see the strong correlation between the open flux and the solar potential field. Sorry, the solar potential field. Right. Okay, so it's very clear, no? The linear correlation.
Yeah, a little bit of noise in there, but
the lower panel of this figure.
Okay.
So we
Good.
use the combination of the different data set in order to create a unique reconstruction of the solar activity in the past, in the last 1,000 years.
Cool. Very cool. Okay, I'm with you.
It's a very long work, mainly made by our colleagues in nuclear physicists that are able to transform the neutron monitor, the carbon-14 results in open flux. So it's a very long work.
Yes.
We have to take into account the magnetic field of the Earth, the climatology, the biosphere. It's a very long work.
It's a lot of parts to that one. Yep. Good. Okay.
So I would like to explain very briefly figure 3.
Figure 3.
Yeah.
Okay, let's pop up. Okay, figure 2, annual values, and now we get into the flux. Okay, magnetic field flux.
So as I was saying, the open flux F0 is our main proxy. And this proxy that we're using in particular dates back from about 1,000 years ago, but it stops at about 1900. And so we wanted to have data that cover more recent times. And what we did is that we used this linear relation that Francesco has discussed before with the modulation potential. Because for the modulation potential, we have more recent data. And so what you see here is exactly what I was talking about. We were able to reconstruct the open flux from the 1900 to up to the present, which is the blue line. And instead in red, we have direct measurements, results from measurements that were published in 2017 by Owens. But these are we spoke over about like the last roughly 50 years. And so, but as you can see, our model seems to
pretty good.
Pretty well.
Pretty good. A little bit there. But overall, very nice. Good. Okay.
So,
okay, I'm with you.
Okay, so now we need another step. And the other step is to try to extract from this signal the long-term variability of the sun. So you understand that the solar constant is not constant at all. And then we have to measure to recover the long-term variability, avoiding to consider the famous 11-year and 22 years cycle of the sun. So we use the EMD, the empirical mode decomposition. The empirical mode decomposition is a signal processing techniques that decompose the signal, in our case, the open solar magnetic flux, in different oscillatory components.
Okay.
If you can move to figure 4, probably I can explain
Figure
better.
4. Okay, figure 4. Yeah, figure 4. Okay, and the Hilbert spectral, couple of equations, and figure 4. These are the IMFs. Okay,
very good. Fine. Okay, the last one, the bottom right panel is the signal that we use to start the process of decomposition in different components, and the reconstructed one. The red is the original signal. The blue signal, the blue line, is the reconstructed line. Okay.
Yes.
How can reconstruct this blue line? We decompose the original signal in intrinsic mode function, IMFs. The function reported in all the boxes in this figure. So the IMF1, IMF2, blah, 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 until residual. Each panel represents a particular range or frequencies. The higher frequencies means are related to the smaller numbers. So 1 is the higher frequency, and then we move toward the residual one. So it's very useful in the original data, scientific data, because the decomposition is not made using imposed functions, but the empirical decomposition means that we use the signal itself in order to recover the different function able to decompose in particular frequencies.
I'm with you. Okay.
So we eliminate the IMF1, IMF2. I don't remember. It's also IMF3. I'm sorry.
We'll say 3. We'll say 3.
In the papers.
We'll say the high frequency stuff up to 3. Okay.
In order to eliminate the higher frequencies and to reconstruct the long-term variability of the sun.
I'm with you. Cool. Good. Yes. Okay.
So at this point, we have the capability to try to reconstruct the signal, but we need the help of Valentina.
Okay, with short time, we use equation 3. Can you...
Yeah, let's back up a little bit. Some equations. So here we go.
Equation 3, okay. Each solar cycle over 11 years, so we use this functional form. That has a quadratic growth and an exponential cutoff in the time. Initially, we have 2 parameters, TS and TD, but we can able to reduce it to only one, because TS and TD correlate to each other. This is because TD is a rising time and is linked to the duration of the cycle. TS determines the intensity of the cycle, and it's well known that a stronger cycle corresponding to short time cycle. So TD and TS are correlated, and in this way we have for a single cycle a single parameter, or TS or TD or a combination of them. In particular, we define exactly this parameter PK as the relation of quadratic relation of between TD and TS. So
Okay. I'm with
We
you.
can found a correlation between PK and open magnetic field.
Yes.
This correlation is shown in figure
6.
6.
Figure
please,
6. Okay, keep that in mind, and we'll slide down to figure 6
Perfect.
and figure 6.
So,
Here we go. PK versus
okay,
this
so
one.
we have this correlation for PK for sunspot and a value of
F0.
of F0 integrated over the corresponding cycle.
yes.
So we can go back in the time using this relation for all cycles along the millennium.
Pretty good.
The flash coverage is obtained by spot by using a power law in equation
6.
It's the figure 5. If
Okay.
you can go up a little bit.
Sure. Figure 5. Let's do
There
that
you go.
first.
So in this way, we have the component corresponding to the short time, in particular 11 or 22 years.
Aha, aha, aha. Okay.
So we have all for reconstruction
Okay.
of PSI.
Let's slide up to figure or equation 6. Let's take a look at that. So we got
And this relation equation 6.
boom, 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 and boom. Okay, so this is your correlation. It's a linear fit. I'm with you.
Okay.
Okay.
Perfect.
Okay, so at this point we have all the ingredients to perform our reconstruction. So if you go toward the end of the article, I don't remember the
Figure 7, figure
Yeah, I
8.
would like to go to what is maybe a question. Yes, here. So our model is based, as I said before, on the empirical evidence that solar radiance variations are modulating magnetic activity. A lot of models are based on, basically all models are based on this assumption, but they all different in these details, and I would like to point out now. So let's start with equation 9.
Yes.
Equation 9 tells us that the irradiance represented here with the letter F as a function of time is given by the sum of the single contribution, barometric contribution, radial contribution of single magnetic features, here as F with J, and their relative area alpha J that varies with time. So the assumption is that the specific radiance and energy emitted by these structures does not change with time, but what is changing is their area coverage.
Got it. Got it. Okay.
Now, I would like to go a little bit down to one of our final equations. So we'll have to get soon to the point.
Okay.
So down.
Boom, 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 boom.
Lower.
10? Or
Yeah.
equations? You want the
even more down. So equation 15.
15, sorry.
14. Yeah. Here equation 15.
Yep. Sorry.
Yeah.
Okay.
So up. There it is. Yes.
Yeah.
Okay.
Let's have a little bandwidth
So,
lag. Oh.
Yeah. So this equation, delta with F is the relative variation of the irradiance over time with respect to an irradiance measured with a minimum of quite. That is our reference.
Yes. Okay.
We have alpha with F and alpha with S are the area of Faculty and sunspot.
Yes.
And we have them already because Valentina has told us how we have reconstructed them back in time using our proxies. So
Cool.
then we have delta with S and delta Fn, which are the relative contributions of Faculty and sunspot, Faculty and sunspot,
Yes.
which we don't have at this point in time. Okay.
Okay.
Then we have another component, Cn, which is in our model after some algebra, which is explained here in the paper. I'm not want to go into these details.
We don't need to do algebra here. Okay.
But Cn represents the contribution of the network weighted by this area during a period of minimum.
Cool. Okay. I'm with you.
Now,
We got C.
now we have in this model also another, in our model, we suppose that this component, this network component changes with time, which is the uniqueness on our method.
Okay.
Other methods they do not introduce this long-term component, or some others have supposed that there's a long-term component, but they have to believe with the quiet sun. Instead, we say, in our model, we suppose that it's this network component or quiet sun network that is changing, whatever you want to call it.
Yes.
So now we have three things. First things, actually three things that we don't know, which are the specific contributions, contrast of Fagunen network, and then the variable CN. And then there is also the disnormalization factor, which is a normalization factor that allows us to relate these long-term components that we have estimated through the EMD analysis of the open flux to the side.
Okay.
So these are very different quantities. They need to be related.
Okay.
So how do we do this? Okay. So we estimate CN, delta with Fn, and delta S using modern measurements of solar irradiance.
Yes.
The way we do that is that we use a composite. Basically, some measurements of TSI taken during the last 3 decades, roughly through the last decades, and we fit cycle by cycle using the formula in equation 13, in which we are not taking into account this long-term component.
Okay.
So the idea is that cycle by cycle, this long-term component is not affecting the irradiance prediction.
Okay.
So cycle by cycle, we only have natural sunspot and Fagunen. And so through these fits, we can estimate the two delta values and CN, which are there that you see here represented. And the good thing is that we have very good agreement with these estimates and independent estimates performed with other instruments and presented individually.
Okay.
So
cool.
now we have these three components. We only need this NMR that can help us to connect this long-term component as we estimate to the empirical mode decomposition with modern invariance measurements.
Yeah.
The way we do that is that we fit now this formula 14 to the whole measurement, not cycle by cycle, but the whole thing. And the other thing that is very unique of our method is that then, so in this way, we can estimate that depth, which is basically is a variation.
That's how you get back to 1,000, yeah.
Yeah, but we need also the absolute value. And the way we do that is again through the whole PSI.
Yes.
Instead, others has taken this value as a fixed value, taken doing an arbitrary time of minimum.
Okay.
This is the value that we got, and it's a little bit lower than the values of the gradients that we measured at modern times in times of minima. So if you go down to the last figure of the paper.
Okay, figure 10. Let's go to figure 10. So this is the money shot. This is the important plot.
Yeah, so here we show our the models that we've been using the model that just explained, and Francesco will comment on it.
Yeah, our main problem is that we have not defined a theory able to explain the behavior of the sun introducing this large minima, Oort, Wolf, Sporer, Maunder.
Yes.
So we have a classical 11 or 12, 2, if you consider the magnetic field, solar cycles, but it seems that the sun modulate also with a very important minima. Why we want to study this, or we believe that it's important to study the solar minima, because we will try to correlate the behavior of the sun in the past. Not very important. You can see that we measure a little bit more than 2 watts per square meter, but for a long time. So what is the response of the Earth climate to this long-term variability? So we want to investigate the possible interaction of the solar variability, long-term variability, with the response of the Earth climate. Okay. In particular, we focus on the Maunder minimum, and then we start to study the Maunder minimum effect using our reconstruction, but also the reconstruction of other authors, because there is a range of it's science. So in the science, we have a different reconstruction, different idea or hypothesis, And then we use a different reconstruction, in particular our reconstruction, to investigate the behavior using the climate models of the Earth climate.
I'm with you. Yes.
In particular, we found climate sensitivity, so the response to the TSI variation, in our case, of 0.13 Kelvin for watt square meter.
Okay.
That's an important point. It's not very large, but the problem is the Earth is not homogeneous with oceans, lands, and so on. And then the response of the different part, the regional part of the Earth are different. So we believe that the little ice age actually is not a global variation of the Earth climate, but a regional response in particular regions of the Earth. In particular, high latitudes of both hemispheres, it seems that we have amplified the response 14–60% more than the global response.
Got it.
This is a way in order to calibrate our climatic models. This is very important because, you know, we are in a period where the global warming is important fact.
Yeah.
Paper does not explain the global warming. Global warming is another problem, is anthropogenic origin. But this one can be used to study the past of the Earth when the anthropogenic effect are not present or reduced, in order to calibrate our models.
Yes.
So this is also a little step in the future, because it's an argument, an issue that we are studying at the moment.
Cool. Very cool.
So I don't know if Serena or Valentina want to say about the reconstruction in the far past. I don't know.
Yeah, so the idea is that we also intend to reconstruct spectral irradiance using this kind of approach or similar approach.
Oh, right.
Irradiance is important because especially the UV that's got a big effect on the Earth's atmosphere and the quantity that regulates molecular oxygen.
That's true.
Also,
okay. Yeah.
Yeah, it's sort of formed in
Sure.
And then we also intend to estimate far more back these estimates, probably go back about 8,000 years. Probably about 10,000 years.
10,000 years.
Yeah,
Yes.
about 10,000 years.
Very cool.
No, it's good because it's the beginning of history of the humanity, you know?
Yeah.
The history starts more or less 10,000 years ago.
Thereabouts.
This means to span all the history of the Earth, of the people of the Earth. So not bad.
For example.
It's far. It's not the sun is not a galaxy. It's not very famous but it's very important in some sense, in the only astrophysical object very important for the life of the Earth. So why not study the sun?
Very cool. Very good. Beautiful, beautiful work. Beautiful. Okay, and then we have that. We end up with that. So the TSI and figure 10 is the money shot. And Valentina and Serena and Francesco, I want to thank you so much for walking us through your very awesome article. Thanks.
Thank you.
Thank you.
We thank you for the invitation. Yeah.
Sure. And so you kind of mentioned it a little bit there toward the end. And let me just push on that a little bit. Where do you think we go over the next couple of years on this research? You mentioned going to 10,000 years. Will we see an article in a few years going back 10,000 years? Is there additional wavelengths that might be useful to cover? Just sort of, what are the next steps? Where do we go from here, given the published article?
Yeah, as I was saying before, actually, we really started and releasing Irradiance in the we already have some articles published where we're using slightly different approaches, so it will be better, and it really allows us to go much further back into the past. So our intention is to use to look at medium UV, UV, and look at other indices as radiance in the past, I wanted to mention that looking at these UV indices is important also because they allow us to make a parallelism and try to understand also what other stars are doing.
Okay.
Particular calcium, we really perform the reconstruction of calcium, but we would like to study much back in the past because of the connection here is with the Mount Wilson data, which monitored other stars other than the sun for decades or something like that. So, and there are more instruments that will come online that will look at stars, we monitor them in UV. So I think that not in the next 2 years, but in the next maybe 10 years, we'll see much more research that connects what is the variability or the UV of the sun connected to the variability of other stars.
Very cool. Very cool. Very nice. Beautiful. Well, it'll be really exciting to see this develop over the next few years. We'll call it a few years. Very cool.
Yeah. The difficulty is if you want to go back of 10,000 years, we have to move from carbon-14 to beryllium-10.
Right.
And it's more complicated. We have to take into account the variability of the Earth magnetic field, the entering the game of the different interactions.
Yes.
So there are more difficulties from the point of view of the reconstruction of the solar activity in the past. But it's important because we can study also the effect, as Serena told us, of the UV. The UV modulated the ozone. The UV is important for our life on the Earth because the DNA responds to the UV variability.
Yes.
So we need to involve in this research other scientists, of biologists and climatologists, geophysicists. And this is the interesting part of the geophysics because we need more interaction of scientists coming from different institutions. No, it's very exciting. It's related to our life.
Yeah. So. Very cool. Very nice. All righty. Valentina, Serena, Francesco, thank you so much once again.
Thank you.
Thank you.
Thank you.
All right. And I hope that made your astronomy day, or at least your 1,000 years solar astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.
Bye.
Bye.